Hello everyone, welcome, and today we're going to look at isomers, especially organic compounds in AS chemistry. So, structural isomers are basically when you have the same molecular formula, but you have a different structural formula. And there's three main types we need to learn about, which we'll look into. First is chain isomerism, then positional, and then functional group isomerism. So let's look at chain isomerism. So this occurs when you have the same molecular formula, but the longest hydrocarbon chain is no longer the same. So let's take the example of pentane. Pentane is what? C, 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 right? And then there's the hydrogens, but we won't worry about that. This is one form. However, there's another form of writing pentane, which is 2,2-dimethylpropane. So there's the longest group is a propane, and then we can take a C over here and then a C over here. So the second one. So this is dimethylpropane. So this shows that this is chain isomerism because the longest hydrocarbon chain has been changed shapes now. So now let us look into positional isomers. So this is occurs when there's from differences in the position of a functional group in each isomers. This is different to functional isomers, just be careful of that. So this can happen in basically any any alcohol group easily. So let's take pentanol. So we have CCC and then OH. This is one version of pentanol. Another version can be CCO and then C, because this will have another H over here. This will be the same. Oh, sorry. This will be the same molecular formula as this. However, it has a different positional, so we have a different naming, and it's an isomer. Now, finally, let us look at functional group isomers, which occurs when there are different functional groups which have the same molecular formula, and these are very common in aldehydes and ketones. So let's take an example. Imagine I have this, and then I have oxygen over here and then hydrogen over here. So what is this? This is an aldehyde, right? So this would be propanal, right? Since it's 3 carbons, the longest change is 3. Now, however, if we look at it, we can also make a ketone from this. So what is a ketone? It's basically when it's in the middle of 2 carbons. So C, C, O, C. And if you check, you'll have the same amount of hydrogens available in total. So you have the same amount of hydrogens available in total at the end. So this is a functional group isomer, since this over here is an aldehyde and this over here is a ketone, so that's different naming also. Now let's look at the more complex one, which is stereoisms, which is basically when the compounds are the same atoms connected to each other, but they're arranged in different ways in shapes. So there's 2 types, geometrical and optical. The second one is the harder one, which is optical, which is much harder to see. So let us look into what is geometrical isomerism first. So this, as you need to know, it will only happen in double bonds. So this happens when cis-transomers have the same functional group, on the same side of the double bond, and trans isomers have this functional group on the different side of a carbon double bond. So let's take the example of 1,2-ethene. So I have a carbon double bond. I have hydrogen here, chlorine here, hydrogen here, chlorine here. So this, isn't that. It's 1,2-dichloroethene. So over here, we can see this is the carbon ring. This is a double bond. And I can see these are on the same side. And when it's on the same side, it's called cis. So the name of this would be cis-2-dichloroethene. However, if I draw this again, like this, and this over here, we can see that the chlorines are on different sides of the carbon ring. This is why it'll be called trans-dichloroethene. So we know this is what we're gonna do practice with 1,2,3-trihydroxybutanol. With the but, we know it has 4 carbons and it's an al, so it's the aldehyde group. So C, 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 and it's an aldehyde, so we put an oxygen over here and a hydrogen over here. and it's 1,2,3 trihydroxyl. So we need to put a OH group in all of these. OH, OH, and then put an OH over here. And we need to fill in the remaining carbons, so it has 4 bonds each. And over here. So I want you guys to try finding the chiral centers. So I hope you guys tried. So the chiral centers over here will be this and this. Why? This over here, there's a hydrogen here, there's a hydroxide over here, there's another carbon chain over here which is different to this carbon chain, which will make it a chiral center. And same over here. It cannot be this one because even though there's different bonds, it does not have 4 different group atoms are attached to it. And over here it can't be because there's 2 hydrogens. So now that we learned chiral centers, we can learn about optical isomers. So enantiomers are basically mirror images of each other. This is a keyword we need to know. And enantiomers are non-superimposable, so they cannot be put on top of each other. So let's take the example of 1-bromoethanol. So it is carbon over here. We have a H normally. We have a bromine. We have a hydroxy, and it's an ethanol. So CH3. So this is our enantiomer. This is our first enantiomer, and this is a chiral carbon. So we can have an optical isomer. How do you draw optical isomer? Just basically for each carbon, make it into their simplified chain. So it's 1 bond in total around the thing at all. Now draw a mirror. Imagine you draw a line and start drawing it from the closest side. So there'll be HO carbon. We have hydrogen over here. We have bromine over here, and we have CH3 here. So this is the second enantiomer of the carbon. Okay. So this is how you draw optical isomers. Now let us take an example. So let us take the example of this question. So we need to draw the displayed formula, the skeletal formula, you don't have to worry about that too much, of 2-chloropropanal. So this is a what? So we have C, 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 and it's an Al, so we have a hydroxide, we have a double bond oxygen with a hydrogen, and the chlorine is on the second carbon, so this is chlorine over here, and we can just fill in the remaining of the bonds, and this would be displayed formula of 2-chloropropanal. And if you want, you can draw the skeletal formula. This would just be the 1 carbon here, 2 carbon here, 3 carbon over here. You have a chlorine over here, and we would have a double bond oxygen over there. Now let's try naming this one. We need to find the longest chain in this, which is just this, and obviously we will of course start with the starting carbon to be near the group. So this is already pentanol, right over here. The methyl group is on the second one, and the bromine is on the third one. So we'll have 3 bromo, and then 2 methyl. Sorry for the writing. Pentanol. I'll put it up on the screen over here. It's 3 bromo, 2 methyl, 3 pentanol, and likewise you can draw the skeletal formula, which you don't have to worry about. Now, let us do a structured question. There are many different chemicals which have the same molecular formula but different arrangements of atoms in 3-dimensional space. That's a stereoisomer. Name the shortest Chirality to have a structural isomer and their isomer. The structural isomers is when they're the same molecular formula but different structural formula. And this will be butane. So it will be C4H10. And what would be the isomer? So firstly, you just have 1 butane. And another one, you can have another one like this. So it would be 2 methyl. Again, this will be up on the screen. There will be 2 methyl, and then pentane. Propane. Cut that out. 2 methyl propane. This would be the 2 structural isomers. And what type of isomerism is this? The longest carbon chain has changed. Hence, this is chain isomerism. Now let's look at the next part. C4H8 butene has several isomers. Name the homogeneous series that C4H8 belongs to. Obviously, this is alkenes. Draw the skeletal formula of 2 cyclic isomers and C4A that shows cis and trans isomerisms. You guys don't have to worry about this since we haven't learned this, but we will do the C4H8 bit. So when does this happen? This will happen around the double bond. So you have a C double bond C, we'll have C over here, and then one to show the cis one, it has to be on the same side. So I've put my other carbon over here and the hydrogen will be on the other side. And to the trans one, I will just do this and I put one carbon over here and one carbon over here. And they can be interchanged, but these will be the cis and trans isomers. There are two unsaturated C4H isomers that do not show cis-trans isomerism. Name these isomers, but where they do not show cis-trans isomerism. So for the two unsaturated isomers, firstly we can just have but 1-ene. So if we draw it out, C, the carbon one will be here, C, and then C. Over here, obviously, one carbon will have two hydrogens, and we just cannot be able to draw. We will not be able to draw the. This will not have cis-trans and doesn't have a functional group, and the other one can be 1-metapropene. So if we draw over here, and then we have C over here. Again, one carbon has two methyl group. This carbon has two methyl groups, so we won't be able to draw a cis or trans isomerism over here. So let's move on to the next question. So draw the display formula of the following compound and explain where appropriately identify any chiral centers. So this again is just seeing your ability to draw these compounds. Since identify chiral centers is very easy, I will just do one. I'll do the first one, and you guys should be able to do the other one. So we can see it is hex and 3 all. So it's hex. So 1, 2, 3, 4, 5, 6, and it's on the third carbon. So the all will be over here, and then on the second and fourth carbon there is a methyl group. So we can draw a CH3 over here, and we can draw a CH3 over here. So we can easily see which carbons are chiral and which are not. So over here, it cannot be these ones because they're always bonded to a hydrogen. Same for this one. Over here, it is bonded to CH3C CH3 group. That is a chiral carbon because it is different for each side. This is a chiral carbon. This again is a chiral carbon, and this again is a chiral carbon. These all have different, 4 different bonds, and they're all different to each other. So we can take these. Now let's just move on to the next final question, which is 1-bromopropane 1-ol exhibits optical isomerism. Draw 3 representations of the 2 enantiomers of 1-bromopropane 1-ol. So firstly, let's draw the diagram of what this would look like. So we would have CCC, since it's propane, and it's on the first one, so we'll just take it over here. And looking at that, it's also the bromine is also on the same one. So, and there'd be hydrogen over here, and there'd be hydrogen. So based on this, we can already clearly see which will be the chiral carbon. This is a chiral carbon, so there are 4 different bonds. So let's just draw it in the notation I told you guys to. So this would be C. Everything else just needs to be condensed down. This would be 1, 2, 3, 4, 5. C2H5. And how to show you guys? Just draw a straight line over here. So the diagrams, this would be one enantiomer. Remember, the original one is also an enantiomer, and then when we draw a line, it would be HOCBr. You don't need to change the shapes of it or anything. And then C2H5. Ignore that. So this would be the second enantiomer of bromoethene propane 1-ol. And you guys don't have to worry about whether it's going into the page or out of the page. We'll cover that later. And I hope you guys enjoyed this video and found it useful. And I wish you guys the best of luck